Decades ago, automating a factory floor meant dealing with massive, rigid banks of physical electrical relays. Compare that physical chaos to the high-speed orchestration of modern automated manufacturing. But machines lack innate intelligence. A robotic arm doesn't know what a box is. It's just a collection of metal and motors. To make it work, an engineer has to translate the laws of physical motion into exact digital instructions. For complex high-speed conveyor systems, that translation happens inside programmable logic controllers, or PLCs, using software environments like Alan Bradley's Studio 5000 Logics Designer. We are no longer routing physical copper wires to control a machine. We are architecting digital logic. Before we can write a single line of code, we have to bridge the physical and digital domains. We need a way to map a piece of hardware, like a photosensor looking for boxes, into the software. Modern PLCs use symbolic memory known as controller tags. Here, a physical wire from a sensor morphs into a digital label, like sensor 01. As physical items slide past the sensor, the tag state rapidly toggles between a binary 0 and 1. These tags form the essential vocabulary of the machine. They give the physical world a dynamic digital name the software can track. Let's put that vocabulary to work. A fast-moving cardboard box slides down the conveyor and breaks a laser beam. If we rely on a standard digital input, the software registers an on state for the entire duration the box blocks the light. In a high-speed system, that single long blockage can be misinterpreted as hundreds of false counts. To solve this, we use an instruction called a one-shot rising, or OSR. It takes that wide, continuous on signal and converts it into a single razor-thin pulse the exact millisecond the box arrives. The inverse, a one-shot falling instruction, triggers a second pulse precisely when the box leaves the beam. This edge detection logic forces a sloppy, continuous physical blockage to be recognized by the controller as a single controllable transactional event. Now that we have precise events, the boxes clear the laser and enter a closed holding buffer, where we need to track live inventory. We take that one-shot rising arrival pulse and tie it to a counter up instruction. Every time that vertical pulse hits, our digital buffer variable increments exactly by 1 unit. When a box leaves the holding area, the exit pulse hits a counter down instruction, which subtracts from that exact same variable. By pairing these opposing instructions, the PLC maintains a constant live net total of the physical inventory inside the buffer, requiring zero manual oversight. Next, we have to physically sort the inventory. We establish a physical rule. The heavy diverter gate must open only when exactly 5 boxes are ready in the buffer. We execute this using compare and equal blocks. The logic constantly weighs our live counter data against a fixed numerical value of 5, turning true only when the numbers perfectly match. But we have a secondary problem. Software makes decisions in milliseconds, but the heavy mechanical gate needs exactly 3 seconds to physically swing open, let the boxes pass, and close. To bridge this gap, we use a timer on delay, or TON instruction. This forces the system to hold the output state open for precisely 3,000 milliseconds to accommodate the real-world mechanical lag. Comparison logic dictates the exact moment a decision is made, and timing instructions govern how that decision survives in the physical world. A single diverter gate is easy to track, but as a facility scales up to miles of conveyors, putting all that logic into one continuous file makes the code completely unreadable. We solve this architectural problem using the jump to subroutine, or JSR instruction. We isolate specific tasks, branching our main routine off into self-contained logic blocks for sorting or motor drives. The main routine now acts as a supervisor. It selectively pings subroutines to execute only when a physical event requires it. Utilizing subroutines takes an amateur string of code and organizes it into a professional, scalable industrial architecture. When all these logical rules align, the entire facility functions as a single coordinated system. But controlling the mechanical conveyor is only the baseline function of a modern PLC in the Industry 4.0 era. The controller's secondary role is acting as a massive data aggregator for the entire enterprise. Using the move instruction, the PLC takes those final batch counts and timer statistics and transfers that data upward, feeding it directly into supervisory systems like Wonderware SCADA or a local HMI. Mastering controller tags and ladder logic allows an engineer to architect the foundational data points that drive global, smart manufacturing. Automated sorting facilities and car assembly lines operate with a level of physical force that is lethal to humans. In these environments, thousands of pounds of solid, heavy steel move at blistering speeds, guided by millimeter precision. Attempting to run this machinery with a consumer operating system would lead to physical destruction. Standard computers run dozens of background processes, which occasionally causes a lag spike to allocate memory or install an update. While a 50-millisecond stutter is a minor annoyance on a laptop, on a conveyor belt it means a 2-ton chassis crashes into a mechanical sorter. Industrial automation relies on hard real-time execution. In this architecture, missing a computation deadline by a fraction of a second is a total system failure. To meet these strict deadlines, engineers use the Programmable Logic Controller, or PLC. This is a ruggedized industrial controller, stripped of all unnecessary software, engineered to read inputs, to calculate logic, and fire outputs in a continuous, unbreakable loop. The PLC functions as a bridge between two realms. On one side is the high-voltage physical world of AC motors and mechanical relays. On the other is the microscopic digital world of binary code. To understand modern manufacturing, we have to look at both sides simultaneously, tracking how physical copper wiring crosses the threshold into a digital scan cycle. Picture a cardboard package traveling down a high-speed conveyor belt. To track its position, the package must break a photoelectric sensor's beam along the rail. Breaking that beam triggers a hardware reaction. The sensor sends exactly 24 volts of electricity down a copper wire to a specific terminal on the PLC's input module, terminal X0. This incoming voltage initiates the first step of the PLC's internal process, the input scan. This diagram illustrates the hardware-to-memory boundary. When 24 volts arrive at the left terminal, the PLC maps it to a dedicated slot in its image table. The physical electricity is digitized, converted into a binary 1, representing an on state in that memory block. The input scan freezes a chaotic physical moment into a perfect digital snapshot. Now, the processor can analyze the state of the factory without the variables changing mid-calculation. The PLC evaluates the snapshot using ladder logic. Reading strictly from left to right, the X0 contact closes upon seeing the sensor's 1, allowing simulated digital power to flow. This current hits the output coil, completing the circuit and activating memory terminal Y70. During the output update phase, the PLC converts that digital 1 at Y70 back into physical electricity at an output terminal. This low-voltage output triggers a physical relay, firing 480 volts of AC power to a motor contactor. The mechanical arm swings instantly, diverting the package. This entire sequence of reading the world, calculating logic, and firing the motor took only 3 milliseconds. The PLC now restarts the cycle, repeating it endlessly to maintain control. In a high-speed assembly line, milliseconds separate normal operation from a catastrophic injury. Consider a scenario where a worker reaches their hand into a moving conveyor belt to clear a jam. To prevent accidents, the machine is guarded by a light curtain, a grid of invisible infrared beams protecting the danger zone. These safety devices use the normally closed principle. Instead of sending a signal during an emergency, they send a constant stream of voltage to the PLC as long as the area is clear. Electricity signifies a safe condition. Inside the program, this constant voltage is the mandatory condition for the main power rail. The ladder logic rung remains true only while the PLC sees that electrical stream. The moment the worker's hand breaks the infrared beam, the circuit is severed. The voltage going into the PLC instantly drops to 0. On the very next millisecond scan cycle, the PLC reads the missing input. The ladder logic evaluates the rung as false and immediately drops all output commands to the motors. Before the heavy machinery can move even an inch toward the worker, the PLC cuts motor power and engages the physical emergency brakes. This reliability comes from the marriage of resilient physical wiring and the relentless digital scan cycle. By reacting to danger faster than human nerves can fire, PLCs create a predictable environment where high-speed machinery can safely operate alongside people.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.